So, last class we started this new chapter on aromaticity. Really the first thing that we've covered is just sort of naming these benzene derivatives here. So everybody just take a second for the sake of practice and name the following molecule for me. Alright, so the benzene ring itself is my parent chain, which means that this thing here is a substituent. What do we call iodine substituents? So this is an iodo group here. It wouldn't matter where around this ring I stuck that iodo group, we would always call that carbon 1. So we omit that locant altogether, and this would be iodobenzene. Right? And that was true for all of our mono-substituted benzene rings. We do not bother to include the locant in the name. All right? So, how are we going to deal with di-substituted benzene rings? All right, we have this special terminology for these di-substituted rings. It's important to get this hammered out here now because it's going to come up over and over again throughout the course. Okay. So if these two substituents, I'm just going to use bromo substituents as an example. Right? If these two bromo groups are located next door to one another, we would call this the ortho isomer. Right? If they're next door neighbors, they are ortho isomers. If instead that other bromine, that second substituent, was one removed, we call this the meta isomer. And if they're located on opposite sides of the ring to one another, we call this the para isomer. All right, so if we're going to name our ortho molecule here, we would put out front of the name, instead of indicating with locants, instead of indicating with numbers, you would just say ortho dibromobenzene. All right, there is a dash between ortho and the remaining part of your name. You can also, you'll see this shorthand where instead of bothering to write the word ortho, they just say O dibromobenzene. All right, so based on analogy, see if you can't name these next two molecules for me. So the next one would just be meta-dibromobenzene, or M-dibromobenzene. And the last one, our para, would be para-dibromobenzene. Or P-dibromobenzene. All right, so we have these ortho, meta, para designations, and they tell you how far apart those two substituents are on your benzene ring. Again, we're going to see this come up not just in nomenclature, but when we start talking about reactions of benzene rings. All right, so again, just to be clear, wherever this first thing is, if the next substituent is located right next door, this is what we call the ortho positions. If it's one removed, this is what we call the meta positions. And if it's on the exact opposite side of the ring, this is the para position. All right, and again, we need a way to remember this here. So sometimes if we can just remember the stupidest thing, it will stick in our head. So instead of OMG, this is OMP. That's our order here, right? In order of increasing distance away from that first substituent, O, M, P. Again, ortho meaning right next door, meta is one removed, and para is on the opposite side of the ring. All right, so we sort of had built this list of rules for our benzene nomenclature here. So now we want to just add for di-substituted. We're going to have to use that ortho, meta, or para designations. Okay, but what if we have tri-substituted, or even more than 3? right, well, let's look at an example. Let's instead say, instead of 2 bromines, we're going to stick 3 of them on this ring. Okay, would these be ortho, meta, or para to one another? Trick question, all right, absolutely, because the ortho, meta, para designates how far apart 2 substituents are. You just simply cannot use it if there are 3 or more on that ring, okay? So instead, what we're going to have to do for our tri-substituted rings is use our normal old ring numbering. And just as always, we want to number such that we have the lowest possible numbers in our name. All right, so see if you can't figure out how to name this molecule here. As soon as there's 3 or more, you're just going to number your ring just like you would a cyclohexane or something like that. All right, so because this is a ring, I can start anywhere with my numbering, right? And I could go in either direction. All right, so there's actually 6 possible numberings that I could put here. Let's just look at 3 of them. So if I go 1, 2, 3, 4, 5, 6, or let's start down here, 1, 2, 3, 4, 5, 6. And I want to compare these 2 numbering schemes to see which one is correct. I'm going to make a list of the location of those substituents in each one of my numbering schemes, right? Because I want the lowest possible numbers in my name. So in my red numbering scheme, it would be 1, 2, and 4. Those are the location of those bromines. If I pick my blue numbering scheme, it would be 1, 3, and 4. So which one am I going to go with? 1, 2, and 4. I want that red numbering scheme because I want those lowest possible numbers in my name. So then if I'm going to name this molecule here, it would be 1, 2, 4, tri-bromobenzene. Okay, and this is really no different than when we were talking about naming cyclic alkanes. You just want the lowest possible number in your name, right? Really the weird one are these di-substituted benzenes. The idea that we have this new ortho-meta-para designation to indicate how far apart those 2 substituents are. If it's tri-substituted or more, you're going to just number the ring. And we want the lowest possible number in the name. Okay, in this case, our ring was all a bunch of identical substituents. But if not, when we assembled that name, we would just do so as we always do, in alphabetical order. So benzene derivatives. What's going to make benzene derivatives kind of a pain in the butt? If they have just these normal substituents on them, we went over how to do that. But they're what are called the special benzene derivatives. And they're called special benzene derivatives because they have their own special names. All right, so what we're going to do is we're going to take these benzene rings and we're going to put different functional groups on them. Okay, so benzene with a carboxylic acid. This molecule right here has its own special name. This is benzoic acid. Okay. If instead of a carboxylic acid group, I have an aldehyde sticking off of it, this also has a special name. This is benzaldehyde. And if there's an alcohol group sticking off of that ring, this is what's called phenol. All right, we got two more special ones. The first with an ether group. This is anisole. Or if there was an amine group, this is aniline. All right, so I'm going to give you a minute to copy these down. These are these 5 special benzene derivatives. And what's going to be kind of a pain in the butt about them is if we see these functional groups in our molecule on our benzene ring, then these automatically become the parent chain of our molecule. So when we would name these molecules, we're not going to call them something benzene anymore. We're going to refer to their special benzene derivative name. Okay? 3 of them, the 3 up top, not so bad. All right, because benzoic acid has a carboxylic acid group, right? That checks out. Benzaldehyde has an aldehyde group on there. And phenol, we use that OL ending to indicate alcohols. All right, so those ones aren't terribly bad. The last 2, though, anisole and aniline, are terribly similar to one another. All right, so how can we distinguish these? How are we going to keep these separate in our mind? Let's notice that anisole has that O in the name, whereas aniline has that N in the name. All right, so those are the 2 that are going to kind of be the hardest to stick in our brains, but they sound very similar. All right, but we have this little trick that we can use here. Again, anisole with that oxygen in that molecule has an O in the name. Aniline with that amine functional group with its nitrogen has that N in the name. All right, so that's how we can distinguish between those 2. Okay? But again, what's going to make this kind of a pain in the butt is if we see one of these special functional groups on our benzene ring, it's no longer got the parent chain benzene, it's got the parent chain corresponding to the name of that derivative. All right, so let's do some examples here. So first of all, when I look at this molecule here, not only is that benzene ring my parent chain, it's this whole thing now. This whole thing is my parent chain. And what do we call that parent chain? Phenol. All right, so this, including my functional group here, all included in my parent chain. All right, this is a di-substituted ring, so what am I going to have to use? Yeah, ortho, meta, para, that business, right? Anytime there's only two things on that ring, we're going to use that ortho, meta, para. In this case, it's in this case, it's meta. So this would be meta bromophenol. All right, my bromo group is still treated as a substituent, but now that benzene ring plus its alcohol group is considered my parent chain. In our next example, what is our parent chain? Aniline. So this whole thing is my parent chain now. And now I have a tri-substituted ring. So ortho, meta, para, or trick question? Trick question, right? We got to use our numbering for this. Okay. My functional group will always be on carbon 1. All right, so let's just note here our quote-unquote special functional group is always carbon 1. So with our special designation, our special benzene derivative here, we actually only have two possible ways to number this parent chain, going either clockwise or counterclockwise. In this case, going, what would that be? Counterclockwise would be correct. All right, which one am I going to put first, bromo or chloro? Alphabetical order, right? So this would be 2 bromo, 4 chloro. And since that functional group is always carbon 1, we don't bother putting it in there. We'll just run that straight in to the aniline. So we can just note no locant for functional group. Oops. Because it's always carbon 1. All right, so we have our special benzene derivatives here. We're calling them special, all right, because they will become our parent chain. And these we just got to be able to recognize, right? So one of your first assignments for this homework period is just a quiz of being able to spy these benzene derivatives. Kind of the intention is that if you're having trouble memorizing these, you'll just do it over and over and over again until it sticks, right? Because these we just got to know here are special benzene derivatives. All right? Now, if that wasn't fun enough, we also have what we're going to call the not so special benzene derivatives. Okay? These are not so special because they have their own names and we need to be able to recognize, but they do not become any sort of apparent chain when they're combined with other functional groups, or other substituents rather. Okay, so if we put a methyl group on that benzene ring, nobody calls it methyl benzene. It's got its own special name. This is toluene. All right, now if we had another group on there, it wouldn't be our parent chain toluene. Now all of a sudden we would just treat it like we normally would, but this molecule all by itself is called toluene. And if we had two methyl groups on there, this wouldn't be dimethylbenzene. This also has a special name. This is the coolest one of them all. This is xylene. All right, and this is one particular isomer of xylene based on how far apart those two methyl groups are. Which xylene would this be? Meta. So this would be metaxylene, all right? There's also ortho and paraxylene. All right, so just for the sake of completeness, everybody draw me, let's do orthoxylene. So orthoxylene, it doesn't matter which two carbons you pick along that benzene ring, they just got to be next to each other, right? That's what it means to be the ortho, right? To be clear, because I can always pick this molecule up and rotate it around, and it's the exact same molecule. Cool. All right, so let's kind of just update our nomenclature rules here. For our parent chain, we got to include this special case when we have our special benzene derivatives. They are what become our parent chain. All right, I will say that these not so special benzene derivatives, there are some circumstances where they are the parent chain and some where they're not, and I don't really feel like picking that battle, all right? So we're just going to lump them all into this category of not so special, where if you recognize them by themselves, they have these special names we got to know, and if they're paired with anything else, then you just treat them as methyl groups, okay? But don't hate me, I don't make the rules. We do have one sort of exception to that ortho meta para that we got to note. Now, this is so stupid. I don't know why they do this, but there is an exception for when you have non-identical substituents. All right, so just to do two very similar examples here. If we had two identical substituents, like two bromo groups, we already did bromo. Let's do chloro groups. Then we would use our ortho meta para designation. So everybody take a second and just name this molecule based on what we learned. So this would be the para-dichlorobenzene. But if we had two substituents that were non-identical, so I'm going to replace that chloro group on the bottom there with an ethyl group. All right, for non-identical substituents, we don't use ortho, meta, or para. We use our normal numbering. Let's think about this here. I could do blue 1, 2, 3, 4, or I could do red 1, 2, 3, 4. In my blue numbering scheme, I'm 1 and 4. In my red numbering scheme, I'm 1 and 4. So I have a tie. How do we break our ties? Alphabetical order. All right. So in this case here, I'm going to have to think my ethyl group is going to come after my chloro group in alphabetical order. All right, so we're going to pick that blue numbering scheme, red lost in that tie, right? Because again, when we have a tie, and only when we have a tie, do we go to alphabetical order. So 1-chloro, 4-ethyl, benzene. I don't know, I guess they don't want you running substituent names next to one another without numbers in between. I don't know why they do it. Kind of seems stupid. But regardless, this is how we name them when we have non-identical substituents. We're not going to use that ortho-meta-para. We're going to instead just use our numbering. Okay, so fun with nomenclature here. All right, let's get off of nomenclature. That's enough of that. Let's talk about sort of the heart of this chapter here, which is this idea of aromaticity. And what we're going to do is lay out our rules for aromaticity first. We'll talk a little bit more in-depthly about what it means to be aromatic or non-aromatic once we can spy what is aromatic. But we got these rules first here, okay? So benzene being the kind of example of this chapter here is a good example of an aromatic compound, and that is because the molecule meets these two rules, all right? Any molecule that meets these two rules is considered to be an aromatic compound. Okay, so number one, you have to have a fully conjugated ring. All right, so what did we mean by conjugated bonds again? We had that perfect spacing of double bond, single bond, double bond, right? And if we look at benzene, the entire ring is this conjugated network. Okay, we talked about this a little bit at the beginning, but really the key to conjugation is where those pi bond electrons live. They live in these p orbitals that are lined up right next to each other. Well, when we have an entire ring of sp2 hybridized carbons, all of a sudden every single one of them has that p orbital, and so these electrons do not stay localized in one place. They are traveling throughout the entire ring, right? So this network of delocalized pi bonds is essential for this quote-unquote aromaticity here. All right, so benzene meets that qualification of having that fully conjugated ring. All right, how do we spy this? We need a ring of all sp2 hybridized carbons. Okay. Again, with that full ring of sp2 hybridized carbons, these pi electrons aren't going to stay put. They're going to travel around and around and around that ring. They're going to spread themselves out throughout that entire ring structure. All right. The next one, and this one we'll explain it a little bit more. For right now, it's going to seem like it comes out of nowhere here. Okay, is that we need an odd number of delocalized electron pairs. It will make sense a little bit more when we go into it. I mean, it's still kind of bizarre, but it will make a little bit more sense when we start looking at MO diagrams. But yes, you need a specific number of electron pairs that are going to be spinning around and around and around that ring, and it's got to be an odd number, okay? So again, what we're going to do is we're going to look and we're going to say, does this molecule meet rule 1? We got to look, is every single one of these carbons sp2 hybridized? Well, these are about this double bond, these are about this double bond, and these are about this double bond, so yes, this meets rule 1. Rule 1, check. We got that fully conjugated ring. And then we're going to go through and count our number of delocalized electron pairs, our pi bonds here. We have 1, 2, 3. So do we have that odd number of electron pairs? Check, check. This satisfies rule 2. So if a molecule satisfies both rule 1 and 2, it's considered aromatic. Okay. If a molecule fails rule 1, right, it doesn't have that fully conjugated ring, we would classify this as non-aromatic. All right, if it fails rule 1, you're done. The rules are in order for a reason. You don't even move on to rule 2. Fails rule 1, scratch it, non-aromatic. Okay? But if you have a molecule that satisfies rule 1, but fails 2, we call these anti-aromatic. All right, so given our rules and given our classification here, let's put down a few more molecules and see if we can't figure out whether they're aromatic, non-aromatic, or anti-aromatic. All right, so we're going to run out of time here. We'll pick up with this next time, but let's try to do this first one together here. Okay? I need to see if I have a fully conjugated ring, which means that every carbon in that ring has to have that p orbital. So I'm going to look. The carbons about my double bond, these are all indeed sp2 hybridized. All right, but what about this one up top? What's the hybridization? This one would be sp3 hybridized, so it does not have a p orbital that can accept these electrons. This is messing up the whole conjugation of that ring, so So I do not have a fully conjugated ring, and we would classify this as non-aromatic. All right, so that's the name of the game. We're going to apply these two rules to these molecules to classify them as either aromatic, non-aromatic, or anti-aromatic, and we'll pick up with that next time.